base 40. Base 40.
40?
40. On
14?
Yes.
Here?
Yes.
Right. So, did you forget everything you learned?
No.
Okay. Everybody, in our last course, I introduced three types of singularity functions. There are three types of singularity functions. The first one is unit step, the second one unit pulse, and the last one unit ramp. We can look at this figure and we will see the figure feature of the unit step is like this. It's a 90-degree angle here and 90-degree angle here. And for this one, it's an arrow pointed to the sky. And this one is a slope, right?
Yes.
And in China, we use UT or ETT instead of the unit step. This is the figure if we change the value of UT at time t equal to 0. We also can make some delay or some advanced step functions. Just minus t0 means delay. Plus t0 means advance. That means if we minus something, we move this figure to the right hand side for t0. And if we get advanced, we need plus t0. That means we remove this figure to the left hand side for t0. Okay? So, where does this function apply to? If we consider a discontinuous piece functions, that is like a switch in our circuit, okay? A switch will bring in a sudden change of our signal. Here we can look at this function. This one is our Vt. Our Vt is equal to 0 if t is smaller than t0. Then it's equal to v0 if t greater than t0. And we can see the t0 is the same, right? That means the t0 is the time point we change our value. So we can use the step function to instead of the discontinuous piecewise function, we put a new t minus t0 inside because the t0 is the time for change. And the t0 is the same. And we can see if we put the t inside, if the t minus then t0, this part will become 0, right? So the total part will become 0 as well. It is equal to this one. If we put t greater than t0 inside, we'll see this part will be v0, right? No, this part will be 1 actually. This part will be 1. So v0 times 1 will be equal to this one. Okay. Right. Here is a figure which we used to instead of this circuit. In this circuit, we can see we have a switch inside, right? And the switch is closed at t equals 0. At t equals 0, this one will remove to here, and the V0 will be connected into the circuit.
Yes.
And we can see if we put a new t step function inside, that is the same, right?
Yes, ma'am.
So this one is switch voltage sources. We can use the V0 UT instead of this circuit. Similarly, we can use the IT times UT instead of this circuit. And we can see the switch is still here, right? And if we move the switch to here at time t equals 0, it will become this one. It's the same. So if in a circuit we see some sources is equal to Vt times the step function, we must know there will be a switching sign, okay? And we can also put in 0 ut minus something here or ut plus something here. It means
Is that function?
advanced function or a delay function, okay? And we also can, if we do a circuit in simulator, if we want to advance the signal, advance the source, we can put a ut, how to say that, block? It's like a block?
Block diagram.
Like, how to say that?
Even this is the function block.
Yes, it's a block. If we put a block inside, that will be the same as the use of the switch. Okay. The second one is unit impulse function, and we say this one is the arrow pointed to the sky. Okay, it looks like this. And for this one, and at t equals 0, our delta t is equal to infinity. Right. So if we put our step function inside and take a derivative of it, we'll find this one will become 0 if t is less than 0. It will become to infinity if t equal to 0. It will become 0 if t greater than 0. So we have a point that the delta t, the impulse function, is a derivative of the step function. Okay. And we also can see the property of this unit impulse. It is a very short duration pulse of unit area. That means here, if we take a short period around the 0, and here we take a 0 minus, here we take a 0 plus, and we can get a small block here. And if we integrated the delta t from 0 minus to 0 plus, the value or the area of this block is 1. This one is an important property of the unit impulse. Here, 0 minus means the time just before t equals 0. It is very close to 0, okay? But it's still on the left-hand side of the axis. And 0 plus, similarly, it means a time point just after t equals 0, but it's still close to t equals 0, okay? And we say the unit impulse has range 1. Here, I put the example here. I put a 5 times the impulse function, but here it's not delta t, okay? It's delta t plus something. What does this mean? Plus t
Advanced.
means
Advanced to
yes, it means advanced. We move the figure
left
to
side.
the left side. Okay, you can see here it's plus 2. So we moved from here to the left hand side for 2, 1, and 2. Okay, so here we have 10 strange times delta t. So here we don't have delay. So this one is at t equals 0. Similarly, here the strange is minus 4.
This is delay, so let's
Yes, it's a delay because our t is minus 3. It's a delay.
Yes.
Minus means we remove
Right
to the right hand side. So it's opposite to the sign actually, right?
Yes.
So in our mind, generally, if we minus, it should be to the left hand side, but actually it's not. If it's minus, we
Right.
move it to the opposite side of the gear, okay?
Yes, ma'am.
The third one is the sampling or safety property of the delta. This one is important property for the impulse function. For any function ft, we integrated it with the impulse function delta t, and we can write a function like this: ft any function times of delta t. T minus t0 means what? Means this one, the t is equal to t0, right?
Yes.
The impulse function is there. If we integrate it from a to b, the value will be the function of f at t equal to 0. Why? Because this one is always equal to 0 except the point t equal to 0, right? So their product just has non-zero value at t equal to t0. So we can derive this function. But here we should notice, the thing we should notice is the limit of the integration. The limitation of the integration is from a to b. Actually, the a and b can be any value, okay? It can be any value. We don't have any limit to the integration limit. Right? And here is derivation, because this one times this one, we just have the ft0 has value. For others, we don't have value. And then the ft0 will be a constant, right? If we do any integration, if this one is a constant, we can put it out of the integration, right? And we just do the integration for delta. For this delta, we know the value is the area, right? The area is always equal to 1, right? So we derive this one is the f of t0. So we found if we want to find one point of the ft, we just need to product this one with the impulse function, right? And then we can find out the point we want. So this one, well, we are saying this one is the CT property. This one is very important. So in the later study, in some of other courses, the CT property is always used to prove some theorem or property, okay? So there is a special case because we didn't put any limit for a and b. So the a and b can be 0 minus and 0 plus. And we will know the t0 will be 0 here, right? So the value of this one will be f0. That means if we want to find the value of t equal to 0, and we just put this one, ft times the delta t, and do this integration, okay? Now we're going to go for this example 7.9. We evaluate the following integrals involving the impulse function, okay? The first one is like this one. So actually, this part, t squared plus 40 minus 2, is actually the fx, right? And this one is the impulse function, right? So we know if this one is fx, this one will be ft0, right?
Yes.
So what is our t0?
This is t0 equal to 2.
Compare this function and this function. We can get the t0 is equal to 2, right?
Yes, ma'am.
So from the previous function, we can see this one is ft is f2, right? Because it's ft0, right? ft0 is 2, so this one should be f2. So f is this one. If our t equal to 2, we can put it inside, right?
Yes, ma'am.
So 2 squared is 4. 4 times 2 is 8, and minus 2, and we get the value 10.
10.
From this example, we can see we don't care about the integration limit, right? The second one, for this example, we put the limit from minus infinity to infinity. Here, would you please tell me what is ft?
ft, the first ft is e inverse cos t, and second is e
So
inverse
how
sin
many
t.
ft do we have here?
2.
Yeah. In this example, because here is the plus signal, right?
Yes.
So this part is the
One.
first part, and this part is the second part. We can separate this one and this one to 2.
Yes, ma'am.
So, and we can see here, there were
Equal
2 impulse functions here, right?
Yes.
The first one, t0 is 1.
1.
The second one, t0 is minus
Minus
1.
one.
What does this mean?
This
It
first
has
one.
value, but different time, right?
Yes, ma'am.
And here, I use the blue block to point out the
Yes.
ft. So, the first part should be ft0 equal to 1, should be f1, right?
Yes.
So the second part should be
Yeah,
f
minus
minus 1. So, for the first part, the ft is this one, and we can put the t0 equal to 1 inside to get the first part. Similarly, for this one, we put the t equal to t1 equal to minus 1 inside this ft, and we get this part. Then, our job is to finish this calculation, right?
Yes.
We put the t equal to 0 inside, and we get cosine 1, here sine minus 1. And this we have calculator, right?
Yes, ma'am.
This calculator we can easily find the result. Now, please,
Practice.
boys, make this practice, and I will get some water. Okay, do this practice.
Here the phone. Here the phone.
Here we class করতে হবে না okay আমরা ক্লাস করতেছি ম্যাথ করতেছি টাইম করতেছি বললো আমাদের স্টুডেন্ট করেছে কি কি করে আসো ক্লাস আসো
Hi boys,
You finished. It needs 30 seconds left.
clear, right?
28.
Can you tell me your result?
28.
28? Okay. Yeah. 28 is the right result because this one here we can see T0 into minus 3, right?
Yes.
So we just put the minus 3 instead of the T of the FT and we get a result. Okay. And please try the second one.
This answer is minus 1 because 3 by is minus
So
1.
you are finished?
Yes.
Did you finish? Right.
But ma'am is easy.
It's quite easy, right? Okay,
If
so
you
we
see
just
this
pass.
question, you can tell the
Okay, we can continue. Right, and here I put a notice here to say the upper and the lower limits it cannot affect the result because of the shifting property of in-house function. Okay, so we doesn't care about the upper and lower limits of the integration. The third one is the unit ramp function. If we integrate the step function ut and we get with r of t. So for the in-house function, we say we take the derivative of the step function, right?
Yes.
So we know the step function, the one we learned at the first, is the most basic one, right? And then we do the derivative, then we do the integration, we get the ramp. Right, you put the u of lambda inside and take this integration, we'll find that r of t is equal to t times ut. We know if we put a constant t times another step, it will become a figure like this one. Right, so before t equal to 0, it is a straight line, right? All of the value is equal to 0. And after t equal to 0, it becomes a line, right? With a slope, right? The slope is a positive value of t, okay? And we also can have a delayed and advanced function for the ramp function. Similarly, if the sign before the t0 is minus, that means we remove it to the
Left
opposite side, right?
Mm.
So this one means delay, okay? So the delay function is like this, because if we t smaller than t0, still 0, right? And if t greater than 0, the value is this one, is t minus t0. And here, the advanced unit step is similarly just remove, because this one is plus, right? Remove this figure to the left hand side, right? And we get the value. And it is easy to calculate the value of this point. The step impulse and unit ramp functions we have learned in this course, and they are related by differentiations as impulse delta t is the derivative of step function, and the step function is also a derivative of the unit ramp. Can you understand this? Because before this we know the integration of this one is RT, right? So the UT is the derivative of RT.
C over D.
Okay. So here impulse, step, and unit ramp. Okay. We also can use integration to present the relation. Our step UT is the integration of impulse, and our unit ramp is the integration of step. That is the same, okay? For this one and this one, we just show the relation of those three basic singularity functions, okay? And we can understand it by the differentiation, and also we can understand it by the integration. So now we're going to see the 7.5 step response of RC circuit. The step response is a very basic one of our course. The step response of a circuit is its behavior when the excitation. What does the excitation mean?
Excitation branch.
Excitation of a circuit means a source, right? If the excitation is the step function, and this step function can be a voltage or a current source. If it is a voltage source, the source will be Vs times Ut. And here we can see, for the original figure, we can see there is a switch, and we know the time before switch open, the circuit is open, right? So the Vs is equal to, no, the V is equal to 0 before t greater than 0. If we close this switch, the circuit is connected, right? So then our V has value, right? And it's become this figure. So we use the UT to instead of the switch, which change at t equal 0. Similarly, if we put a switch which changed at t equal to t0, so what does the value change? It's t minus t0, right?
Yes.
Okay. And here we have initial voltage of C, V0 here, and we can use the KVL law to calculate. And we get V as UT, right? So we can take the voltage here is the voltage drop between here is equal to the voltage drop between here, okay? And then we get V as UT is equal to the current going inside into here, IR, right? And plus the voltage V here. And here, what is the value of I?
dV by dt. dV over dt. I.
Yes, because we have the capacitor here, so our I
C
is
dV over.
equal to C dV over dt times R.
Yes.
And we can rewrite this function. How to rewrite it? We put the CR, right,
Yes. This.
on the denominator, okay? And then we get this one with CR here, right? And CR here. And we get this equation. This equation. So this equation is in the form of VI, right? V dot is the derivative of V plus RCV, right? Minus Vs over RC in here. So, what is this function? Obviously, it's what type of function? Would you tell me? What type of this function?
No, function.
Differential function.
Yes.
Okay. And here we know our ut is a step function, right?
Yes.
And we can see for a step function, we can use t greater than 0 to instead of it. Because when t greater than 0, our ut is equal to 1, right? So if t greater than 0, we can use this equation instead of this one, and we can get this one. If we rearrange this function, if we remove everything which related to the v to the left hand side, and remove everything which related to the t to the right hand side, we can see for the left hand side, everything is a function of v, right? And right hand side, everything is a function of t, because here the coefficient is constant, right? So we can integrate both sides. For the left hand side, we know our x1 dx integration is equal to log x.
Yes.
Remember?
Yes.
So if we do this integration for the left hand side, it should be log x, right? And here inside we use t minus vs inside, and we change the limits, the upper limit and the lower limit. Vt and vt. Okay? And to the right hand side, here we integrate it from 0 to t. Okay? 这是我在上课没学过，打电话。等会儿。
No problem.
Our v0 is the initial value of v. That means when t equals 0, our v is equal to v0. When t is equal to t, the v is equal to vt, right? So that is the upper and the lower limit for the integration. And then we put the upper bound and lower bound inside. The value will be ln vt minus vs, because here we put it here, right? Minus ln v0 minus vs, because here we use v0 instead of v here. To the right hand side, we can put the t inside, the same, right? And if we put 0 inside, there will be 0. So the right hand side will be this one. We know the ln, another equation, ln b minus ln a minus ln b is equal to ln a over b. We also can say ln a plus ln b is equal to ln a b. Okay? Yeah. So here we use the first one and we put them together, we get this. It's very, very easy. And then the left hand side is the lower function, right? Ln is a function about the e, exponential function. So we can take the exponential of both sides. And the left hand side, if we put e here, the e and the ln will disappear, right?
Yeah.
We just leave this one here, because this one will remove to the front as the coefficient. Okay, and the e ln will be equal to 1. So on the right hand side, if we put the exponential here, it will be like this one. Here we can see there is a tau. Tau is the function of r times c. What is this one?
Time.
This one we called the time constant. What does this mean? Have you ever heard of time constant? From the name we know time constant is something about the time, right? But we can see it's something about time. That means the unit is second. Here we can see it's r times c. If we compare about the unit, we'll find
This is second.
if we time r and c together, the units will be second. The second
Yes,
again.
ma'am.
Okay. So then we can rearrange this function, right? If we remove this part to the right hand side, right, and we rearrange this function to a function about v, can we? Yes, we can.
Yes.
And we know this derivation is about a function greater than t0 because here I put a condition here. If we put t greater than 0, then we have this one. If t is not greater than 0, this part will be 0, right? So if t is smaller than 0, we know from the last figure, if this one is open, you can see this one is an open circuit voltage, right? We know the open circuit voltage, we just remove this one or turn off all of the resistor, right? And then the voltage is the open circuit voltage. So here we can easily get if t is smaller than 0, the circuit is not closed. So the value of V is the open circuit value, is Vs. And if t is greater than 0, and we rearrange this function, we get this one. And this one is important function for us. We call this one as complete response or total response. This definition we need to remember, okay? This one is complete response or total response, okay? Now we're going to look at the complete response. Our V is equal to Vs plus V0 minus Vs times some e to the power of minus t over tau, right? The figure should be like this one, because if our t equals 0, and we will see it should be Vs, right? Before t equals 0, it will be Vs.
Yes.
And after t equals 0, we still have Vs, but we put another, we still have V0, but we put another, because it's V0, we put another Vs inside. Okay. For this equation, we can see we also can rearrange this equation. We put the thing related to the V0 here and the thing related to the Vs here, and we get another definition. Our complete response is equal to the natural response plus the forced response. What is the natural response? Natural response, for the natural response, we don't put any independent source on. We would put all the independent source off, then the source in our circuit is just, actually we say it is the source is not accurate, because we say the capacitor and the inductance they are not source, right?
Yes.
But they are stored
And
storage element. So it also can supply energy. If we put the storage element inside the circuit, we don't have source inside, but because of the energy stored before, we still has response. Okay, response we call the natural response. The second part is the forced response.
for independent.
Forced response means we turn off or not turn off. We set all of the
Natural response.
storage element to 0, okay, and we calculate the forced response, which is the response of the independent source. Walk along, okay, and then we get two parts. The first one is produced by the storage element, like capacitor and inductance, and the second one is produced by the independent source, right? So we know why we can use this. It's because of the superposition theorem, right? Because of the superposition theorem, we treated the storage element as a type of source, and we get the complete response is the storage element which works along, plus the independent source which works along, and put all the response together, we get the complete response. Here I put the explanation of natural response and the forced response. And we should notice the natural response is due to the capacitor or inductors due to the energy stored in it. And the forced response, okay, the forced response is because of the independent source, not here, okay? So to get a conclusion, the complete response can be written at V is equal to V natural plus V force. And then here our natural response Vn is equal to V0 times E minus T over tau. And Vf is Vs plus 1 minus E minus T over tau. Okay, so here we say those two functions has the same part like T
Over tau.
minus E exponential to the power of minus T over tau. Do you know how does it look like? This function. How does it look like? This function is something like this. When T is equal to 0, it tends to infinity. If the time T tends to infinity, this equation tends
0.
to 0. And here we can notice here, that means if our T tends to infinity, this part will be 0. Clear? And if our T times infinity, this part tends to 0, but we still have this part. What does this mean? When T tends to infinity means it's a long, long time, right? So we say this state is a steady state. Okay? So a steady state has a steady state value, right? The steady state value here, we can say is obviously the Vs, right? Clear? So the Vs is the steady state value of a complete response. And then I have a conclusion here. The eventual response of the circuit is to reach Vs after the natural response decays to 0. And we know, actually, did we introduce the time constant before? introduce the time constant before, or we just see it is first time?
First.
Okay, never mind. Now we're going to look some other perspectives. Another way to look at this response is to break it up to the transit response and the steady state response. So what's the difference? We can see for this part, it's more about mathematics. Okay, because it's more about mathematics. But here, we introduce another way, which is more about physics. Okay, another way to look at the response is break it into the transit response and the steady state response. The steady state response I just introduced, right? So we just now look at the transit response. A complete response is equal to the Vs plus V0 minus Vs e minus t over time. This part we call the transient response. This part we call the steady state response. So, before this introduction, we know our complete response, we can separate it like natural response and forced response. And now I introduce another way to understand it. This time we call its transit response and steady state response, right? The complete response can be written as V equal to Vt, T for transient, plus Vss, Ss for steady state. But actually, we know we just change or we just rewrite the function, right? Everything is the same, just because here we can see the complete response has two parts, right? And here we have everything with T0 and everything with Vs. And in this way, we have here everything, no, it's not just with Vs, it's with Vs. But the second one, we have V0 and Vs together, right? The transient of Vt, we just calculated. Sorry, this one is steady state. This one is transient. Wait, I'm making a mistake here. This one transient, this one steady state. Okay? This transient response Vt is the second part. And the steady state response Vss is this one. Because before the analysis we know when t tends to infinity. Okay? This part, when t tends to infinity, this part will become 0, right? So the steady state, the transient response tends to 0. We just have Vs. So the Vs is our steady state response. Okay. If the switch changes position at time t equal to 0 instead of t equal to 0, t0 instead of the t equal to 0, there is a time delay in the response. If we have time delay, if we compare this one with the previous one, we'll find the time delay is here. Okay, so this question, our t is just t. If we have delayed or we have advanced, it will be a change at here. Okay, so it changed to t minus t0, and if we have advanced, it will be t plus 0, okay? And here, we use another notation to instead of the Vss, we use V infinity. Here, infinity means t time tends to infinity, okay? And here we have Vt0 instead of V0, because not every time the initial time is 0. Because we change the initial time from t0 to from the Vt0 to V0, okay? Then here the same Vss, we use V infinity instead of it. So this one is the equation we should remember. Now we'll look at this example 7.10. Okay, in one, we see here is a switch inside this figure, right? This switch is in position A before t equals 0. And after t, the position of the switch is changed to the B, moved to the B after t equals 0. And we should determine the Vt for t greater than 0 and calculate its value at t equals 1.4 seconds. Okay, look at this example. The first step for this question, we need to calculate the V0 with t smaller than V0. Because V0 is the state before we close the switch or we change the switch, right? So if we want to find out the V0, we need analysis the status before t equals 0. So here we notice if we want to calculate the V0, we need to analysis the state before t equals 0. Okay? For this state, our switch is on A. This part is open. Okay? And the conductance is open. The conductance is here. Why? Why our conductance is open?
Because this is capacitance. This is not conductance. Yes, sorry. This is capacitance. So when we think about it, we have to make it.
Now we have this one here, because we know for steady state. We mean for this state, our switch is closed for a long time. We say this capacitor is fully charged. Okay, because this one is a DC source, right?
Yes, ma'am.
If a capacitor is fully charged in a DC circuit, it will be open. Okay, remember?
Yes.
It will be open for steady state. Okay. So actually, our V is equal to the voltage or
5 ohm.
5 ohm.
5 kilo.
So I put here our V is equal to V 5 ohm here. And now you will see this circuit is a simple voltage deviation circuit, right? Here, still remember?
Yes.
The voltage here is equal to the value of 5 over the sum
Yes.
and times the
The
total
total.
voltage. Okay, so we get our V is equal to 15 V or 15 volts. Our V0, we get our V. Okay,
Yes.
so the step 2, we need to calculate the time constant. We already know this circuit is a RC circuit, right?
Yes.
It's RC circuit. We have R here, we have
And
C here.
capacitance.
So it's RC circuit. For RC circuit, our time constant tau is equal to R times C. But we should notice the R is the surrounding resistance RTH. Do you still remember how to calculate the surrounding
Yes, ma'am.
resistance? If we forget, just go back to the previous knowledge, okay? If we calculate the resistance RTH, we can turn off the independent source. Turn off the independent source. Not here. Here, if we calculate time constant, we should put the switch to the position B, and then the left hand side is open,
Yes.
and we just have this part, okay?
Yes.
And for this part, we know if we turn off the 30V, means 30V equal to 0, right? 0 means this one is a wire. Okay,
So RTH equals
so we
4.
short this one. If we short this one,
RTH
and we
equals
just
4.
get this one, right?
Yes.
So our RTH is 4 kΩ. It's really easy, right? Just use the scale we learned before. And our tau is equal to RTH, surrounding equivalent circuit. It's surrounding equivalent circuit, and we get the surrounding resistance. But for our previous study, our Slavonic equivalent circuit we doesn't have capacitor inside, okay? But actually, if we has capacitor inside, it doesn't affect anything, okay? You still can get the RTH, okay? Because for our RC circuit, for the circuit before, we can see we have our C inside, we also have our RTH inside. Right. Okay, so our RTH is equal to 4 k ohm, and our tau, we just put the value of RTH inside, and we can get the value. The tau should be 2 seconds. Okay, after calculation, we get the value of tau, it's 2 seconds. At step 3, we should calculate the time Vs for t greater than 0. No, actually we should calculate the Vs for t equal to 0, so the time is wrong, okay? The time is wrong. After 5 time constant, the C is fully charged. Do I introduce time constant before? I think I introduce the time constant in our last code actually. Because I say the time constant, the unit is second, and it should be all the response should be finished after 3 or 5 time constant. Remember?
Yes.
Okay. So after 5 time constant, the C is fully charged. The capacitor is open, but actually we doesn't care about the time constant because we don't know the move after this time. So actually we don't care about the time constant. Means the VSS, the steady state response is always the same. The time doesn't affect it. Okay. So our V infinity is equal to 30V because here we know our V infinity is the open circuit, right? Because after a long time, this one is fully charged, okay, and the circuit will be open, right? If open, our V infinity is 30V, is equal to this voltage, okay? And step 4, we need to calculate the complete response of RC circuit using this equation. Because we already know the V infinity, right? From the step 3, we have V infinity is 30. And V0, we get it from step 1. Before t equals to 0, we get the V0, and then 30, 15, 30, and then we put the value of tau inside. Because tau is equal to 2, right?
Yes.
So here is 0.5. And then 15 minus 13 is minus 15. And we get the value. Don't forget the t greater than 0. Okay. Every time when we write the complete response, we must know the complete response is for a time period. Okay, it's for a time period. Not just work long, it's for a time period. The step 5, we should calculate the V1 and V4. We already know the time, we already know the complete response of V is in the form of this one. So we just put the value 1 and 4 inside of the t, and we get the value. It's really easy, okay? This one, or this case, is really easy case.
Okay.
Now, have a practice for this one. Come on. The practice 7.10. We need to find out the V. Where is the V? V is the voltage on the capacitor 1/3. Okay? And we assume the switch is open before t equals to 0. And it has been open for a long time. If we close this one at t equals to 0, and we need to calculate Vt. What does this mean? Before this one, we know this part are open, right? This part are open and it already closed for a long time, so this one become an open circuit, right? And after that, if we close this one, we calculate the infinity. If we close this one, then this one, everything is inside the circle,
Yes.
right? And then we calculate the Vs. How to calculate the Vs? After a long time, this one will be fully charged or something, right?
Because this is connected to 15 ohm and 7.
Okay, just work it by yourself.
Roshi.
Okay, come on. I don't want to show you the answer. Okay, come on. Any question?
I have a question for you. Can I calculate out Thevenin when switch is on A?
On anything?
But
Can
you,
you what?
yeah, out Thevenin, out A.
You want to know what?
Okay, can I calculate RTH when switch is
No.
on A?
No. Because our target is for T greater than 0. That is our target. Completely
For
solved.
this one.
Yes, so we cannot calculate the time constant before that. Because if it is RTF for T smaller than 0, so the RC is for T smaller than 0 as well. But our target is T greater than 0. Clear? Okay. You know how to do that? Is it hard? No, it's not hard.
Okay.
Clear, if we want to calculate V0, calculate the value before the switch close. Okay,
Okay.
if this switch is open, we just do this part, and we can draw a figure. If it is not here, just draw a figure before T equals 0. Draw a figure before T equals 0.
Okay.
Yeah?
I can't understand the previous one because one question was how can you make this 3 plus 3 plus 1?
Because the switch is closed for a long time. So if T is smaller than 0, the circuit will be like this. Here, and then drop. Right. And then A, switch A, and the if this one is closed for a long time, this one fully charged. You know what is the meaning of fully charged?
There is a value of given 5.
No, we don't know about it. If the C is fully charged, that's meaning fully open.
Oh, okay.
If this one is open, the circuit will become like this. Yeah. It's the same, right?
So roughly this one roughly. V for V0, how will you V for V2?
Because V0 is the V before T minus 0. It always equal to V. Yeah? Or you can put the V 0 minus. That's the same. That's the same, okay? We have 2 minutes to finish. Right. And draw a figure. No? Before. You draw a figure before it's closed. Before it's closed. Before T. So you should put a T. Draw a figure for T smaller greater than 0, it will tend to this side. They'll become like this. Right? For T0, for V0, is equal to V0 minus. So the minus is bigger on the other side. And because this one is 3, right? When it's very hot, it's good. Equal. So, and then V is still here, should be the VOC should be this one. Yeah. And then we calculated T greater than 0 for VS. But before that, we calculated tau. Because I calculated the second step, we calculated tau. So it should be RTH times C. So what value of RTH? Is the value taken is the value value is C. Take this point, right? So we turn this one, and we turn off the independent source. Turn off means this one the 0 become a wire, this one become a wire, so this one are power. So it should be power the products of this one, right? So RTH is equal to that, and the value of C is actually 1.3. So put it inside, and get out. Here, this one is step 2, this one is step 1, this one is step 3. Now we're going to step 3 and calculate the VS. This VS means a steady state. On the steady state, this one will be volatile. They will open it. Clear? And then we calculate the final voltage of V. The VS is equal to V into still V here, okay? But this one is open, and now we calculate the voltage for those spots, the voltage for those spots. This is the end. This is the end. Clear? Clear, everybody? So, I think you guys doesn't have a good habit. Because we just stopped to learn this method, so the best way is we draw some subfigure, you know what I mean? Draw some subfigure. You can see here, we draw subfigure 1, okay, sub 1, I can see sub 1 here, right? The sub 1 should be a figure before we close. Clear? And we need to draw a subfigure 2. And that subfigure after
Close.
the switch close. We draw it like this. Right?
Like
T
this.
minus 0, T plus 0. Clear? And then the first step 1, just look at this one. Clear? Step 2, look at this one. For step 2 and 3, look at this one. Step 1, look at this one. Because for step 2, we calculate the tau, right? If we calculate the tau, calculate the RTH, we already know this. Calculate the RTH. So how can we calculate the RTH here? We take this point, right? Because we know the surrounding circuit is it's actually it's the R input of this port. So take these 2 points and ignore this one and calculate the RTH. Okay, ignore this one because we can use a V to instead of this one here. So we doesn't care about this one. We just want to know our V. So our V should be, we should calculate our RTH. For these 2 points, our RTH means turn of independent source, and then those 2 parts in parallel. Okay, please. Clear? No. And then okay, this one is okay. So this one is sub figure 1, sub 1. This one is sub figure 2. No. If you draw figure 1, remove this part. Okay, because this one's closed.
No, this another one. Another one, this one. This one is figure 1.
It's the same. Oh no, not the same. Okay. Okay. For the sub 1, remove this part. For the second one, close this one. Okay, we don't want to see any switch again because we get into 2 subfigures, so we don't need to put the switch again. So this part is greater than 0, part T is more than 0. And if you want to calculate the V0, use this figure. For step 2 and step use this figure. When you calculate this figure, our RTH means take the RTH of these 2 points. RTH is to RI input of this port. Yeah, and turn off those 2, and then those 2 are in parallel. And you have like this. Okay, anyone? You must be right, I know. Okay, so we don't wait. I don't waste time to check the result. Okay, so just look at the screen. I will explain this one. So the first one, we know we calculate the V0 with T smaller than V. So for you guys, the best thing is to draw 2 subfigures. One figure for T smaller than 0, another for T greater than 0. For T smaller than 0, we try to calculate the V0. Because our V0 is equal to our V0 minus, okay? So for this one, the condition told us the switch is closed, is open for a long time, right? So the subfigure 1 should be this part, okay? And we already know this one is fully charged. If a capacitor is fully charged, we open this one, right? So our V, the initial value of the V, should be the open circuit voltage of this port. It should be 15. Our V0 equals V0 minus. So I will get this value. For the second one, we calculate time constant. Tau is T greater than 0. If T is greater than 0, and here we can see I put a port 10 instead of the capacitor, right? And we close the circuit, the switch. And actually, from this figure, we need to calculate our surveillance resistance of port 1 and 0. Because we need to calculate the RTH for the port 1, 0. Because the port 1, 0 is V, right? Then we turn off those 2, and we get 2 and 6 are in parallel. Okay. You can imagine if we put a Y instead of this one and put a Y instead of this one, those 2 are in parallel, okay? For this figure, okay? And we get the value, the product over the sum, and we get the RTH is equal to, okay, here I get the wrong value. It's not volts, it's ohm, okay? Here I got a mistake here. And then our tau is always equal to RC. For a RC circuit, it's not an RL circuit. Actually, we have RC circuit, we have RL circuit, and we also have RLC circuit. But here we just discussed the RC circuit.
First
Okay.
order circuit.
Okay, we just discussed the RC circuit here. Put the value of 1.5 inside, and we get the tau is equal to 0.5 seconds. And then we're going to our step 3. For step 3, we still use the figure after t greater than 0. And then when we're going to calculate the Vs. Vs means steady state. Okay? Steady state, a capacitor is fully charged, so it is open. And the circuit is like this one. And we can see for this circuit, we just have 2 simple sources and 2 simple resistance. It's a simple pure resistance circuit. For this type of circuit, with just one loop, we easily applied KVL to get the result. We also can use the voltage division, right? And this one in series. So the total value is 50 plus 75. And here the voltage should be the value of the sum, and we get the value. It's easy, right? So our EV infinity, we can use 15 minus this one, and we also can use the value here. You can take both sides. Okay, it's up to you. You can calculate the V from this loop, and you also can calculate the V from this loop. Okay. So the last step, we calculate the complete response of RC circuit using this one. Because we already get the V infinity for step 3, and we get the V0 from step 1, and we get the tau from step 2. And put this 1, 2, 3 value inside, and we just get the response, the complete response directly. But we should notice, here we have to put t greater than 0 here, because we know the thing we put inside, except the initial value of v, everything is about the time over 0. Okay. So the step 5, calculate the v.5, because for the question is asking us to find out the v.5. That means our t is equal to 0.5. So we just put the 0.5 inside our complete response, right? Because our complete response, this one is a function of t. Okay. So we can easily get the value with our calculator. Okay, have a try this one. And I hope you guys can follow my guidance, okay? The first step, draw 2 figures. Okay, finish this question step by step. The first step, draw 2 figures. Draw 2 figures. Please, draw 2 figures. Draw 2 figures. I hope we can finish chapter 7 and 8 today. It's not possible. I hope I can finish chapter 7 and half of chapter 8. I will try my best, okay? Is it too fast for you? No? So it's fast. But you still can hold it, right? Is it quite fast? You don't want to reply, okay? Just draw 2 figures. Follow my guidance. The natural response and the forced response is quite mathematics because of the superposition theorem. But for this type of steady state and transient state, it's more physics. It's more easy because for the mathematics, it is easy for us to get the steady state value. Okay? Easy to get the steady state value and easy to get the initial value. And the time constant, it's just the coefficient about R and C. It's more easier. Okay. Did you finish? When you finish your figure, show me your hand. Figure. You're okay, no? Do you happy for our course? Do you find you can learn something here?
Hello.
Do you happy with our course?
Result?
Course. Do you happy with our course? With the
I
content?
didn't get my result.
Pardon?
I didn't get my result yesterday. About it.
You don't know how to have a speaker.
No.
This last exam, he don't know his result.
I didn't get your result.
You just got my result. Okay. Anyway, we still have another example. Just follow the step, okay? The step, go figure. Step one, go figure. Go figure. Okay. Why? This one, okay. This one for t greater than 0, smaller than 0. Tell me. What? Smaller than 0, okay?
Yes.
T greater than 0. Let me have a look. Yep. And this switch off. Just like this. And do more analysis. Here, I will see more analysis like this. Clear? Means open this one. Okay? And then do step 1. Do step 1. Okay? Try step 1. Finish figure? Okay. Let's put some more here because it has closed for a long time. So this one is open. Okay? And then open. So this still have to be here because of the limit here. Okay? So we still have to leave it here, but we must now this one open. Okay? I'm happy with this step 1. Finish. So this for step 1, okay? I need 2 figures. This one for t greater than 0, smaller than 0. At any time, draw figure for t smaller than 0. Okay, this one is greater than 0. Draw the figure smaller than 0 first. Okay. Finish? Okay. Okay. And try step 2. Is this one. Another good habit. We put 2 dots here. Okay? Small here. Put 2 dots here. Means this one is the port. Okay? Voltage division. Voltage division. Just like that. Voltage 10 volts here. It should be 20 plus 10. 10 is here, but I will here. Here. This one for me, not for this one, not for this 10, not for this 20. This one will be for this 20. Okay? Here. So this one is 20.
Right?
No, it's wrong. You can see the switch is here. The switch is here. If we don't have the switch, if this one is open, it should be like this. Because this one is not connected. Okay, so this one, and we know it's already fully charged. This one should be fully charged, and this one open. But we still have voltage here, and our V is equal to V20 because the voltage here is equal to voltage here. 10 10. Okay, so, and then we finish the analysis for the first figure. Then for the next one, this one is okay. This one is okay. This one is okay. So now, this one is for t greater than 0, and this one
not TVS Alpha and this how can I will be straight TVS from
We reckon RTH. And our C is 1/3. And here you stick it.
Wonderful.
Yeah.
But here is
This is this one. We just calculate RTH.
oh, I know.
Finish?
These two figures,
You're low here.
you are,
I trust you. That's your right, okay?
no,
Did you finish the step 2? Did you finish step 2?
I can try this practice.
Okay. Step 2. Are you sure? You are catch? Okay. Okay. This is wrong. The calculation is wrong. 30. 20.
Ma'am, I can practice RL
Yeah.
because RC is finished.
Yeah. You can practice others.
RL.
How about your result? You get RTH? This is RTH. RTH means it's close. Yeah? Yeah? Yes. You should be right. And okay, finish your step 3. I didn't try to calculate. You check your calculation, okay? Finish. Step 3. Okay. Did you finish step 2? Right. Did you check the results? Okay. Right. Finish step 3. Step 3, calculate VS. Did you finish step 3? Don't copy my result, okay? Don't copy my result, guys. Don't copy my result. I know you have my PPT, but don't copy my result. Try your best. Because if you copy my result, I don't know if you understand or not. Okay? If you are not understand, you can ask me. It's okay. It's fine. But if you cannot follow me, you cannot follow the following course. So I have to make sure everybody, you know, and then, because we already just have 4 students, right? If you don't understand, you won't come back again. So would you just tell me why he doesn't come?
Yeah, we already called him.
So he dropped my course?
I don't know. What did he reply?
He's sleeping. He don't want to hear. He don't want to see me. Okay. Come on. Did you finish the last question? Finish? Do you want a break? It's already 10. It's already 10. And this figure is for circuit with t smaller than